So this chapter is more on the sun. It's called The Sun is a Nuclear Powerhouse, and we're going to learn a little bit about how the sun works. Talking in part about just general terms like energy and how it moves around and the fundamental particles of the nucleus of an atom, which are responsible for the sun's enormous amount of energy. So the sun, it turns out, is actually a typical star. It looks big to us because it's nearby, but it isn't especially big or small or hot or cold. It isn't in a particularly unique place in the galaxy or in the universe. It's sort of an average star as stars go. We see a lot more stars that are similar to the sun observationally. So we're going to talk a little bit about types of energy. Energy is one of those things that's slippery because it can come in lots of forms. We can see there's chemical energy and kinetic energy and thermal energy and gravitational energy. There's lots more kinds of energy, but we'll just talk about a few of them. So gravitational energy is energy objects have due to their position in a gravitational field. A boulder at the top of a mountain has the potential to do a lot more damage than one at the bottom of the mountain. Kinetic energy is the energy associated with motion. So as that rock rolls down the hill and speeds up or rolls down the mountain, it gains kinetic energy and loses gravitational energy because it gets lower and lower. As it gets lower, it has less gravitational energy, but it has more kinetic energy. So there we would say gravitational energy is being converted into kinetic energy. Thermal energy is associated with heat. If that rock fell really hard and smashed into something, it might get really hot. And chemical energy is stored in chemical bonds. We'll also end up talking about nuclear energy, which is energy stored in the nucleus of atoms. But chemical energy you're familiar with. Gasoline and batteries and things like that store energy in the form of chemical bonds, and we can release them by burning them in a variety of ways. So one of the laws that's involved with energy is called the law of conservation of energy. And basically what that says is if you have an isolated system, you can change your energy from one form to another, but you can't create or destroy energy. So that for that rock on the top of the hill, on the top of a mountain, if you think of that as a system maybe, well, it's got a whole bunch of gravitational energy at the top, and it's kind of stuck with that. It can convert that to kinetic energy by rolling down the hill, and also maybe heat by bouncing into things and crushing them. But the total amount of energy, if you could keep track of all those little bits of energy that it's losing or gaining along the way, would be constant, and that's what conservation of energy says. Conservation of energy is sort of like conservation of money. If your system is isolated, the total amount of money is not changed. You can't create or destroy it. Now, you kind of can with money if you're a government, but that's cheating. You can't do that with energy. So this is just talking about, discuss how energy can be converted. Chemical energy, your car is a machine that converts chemical energy into kinetic energy. The motor takes the gasoline and converts it into heat and uses that to convert into kinetic energy or motion. If you were really able to track all those energies, they would all add up to the same thing at the end of the day. Most things ultimately get converted into heat. So let's talk about the sun. So early discussion of the sun and the earth was really interesting. A few hundred years ago, a guy named James Hutton wrote a book called The Theory of the Earth. He was the first person to really start writing down the geological and fossil evidence that the earth is much older than people were thinking at the time. His statement about the earth, which is sort of become a common quote, is no vestige of a beginning and no prospect of an end. So he was starting to argue for a very ancient earth. He was probably the first person to do it. His work was continued in the 1800s by a guy named Charles Lyell. Charles Lyell, by the way, was an excellent English Victorian writer, and I think you can download his books. And he's a good writer, so it's a pretty easy read. There's not much technical science stuff. And you can see what he was thinking in the 1800s, and it's really kind of fascinating. Like I said, he writes really well, so he's entertaining to read. His book was called Principles of Geology. So Charles Lyell continued to accumulate evidence and arguments for an ancient Earth. These guys were just kind of explorers and looking at sedimentation layers in canyons and deposits in riverbanks and things like that, and were arguing that the Earth had to be much older than what people were suggesting, hundreds of millions of billions of years or billions of years old. Somewhere around the middle of Lyell's time, in the middle 1800s, Charles Darwin proposed a theory of evolution, which also required an ancient Earth. He only got passing support for his arguments from Lyell, who wasn't a big fan of his theory, I don't think, or at least didn't think it was revolutionary. It turns out lots of people in the past had proposed various forms of evolution. What was unique about Darwin was he proposed evolution by natural selection. Even Aristotle suggested evolution. So that's a whole different story, and it's not my field. But it's interesting. So Darwin was also arguing for a very old Earth. Again, hundreds of millions or billions of years old. So the question became, how can the sun be that old? And lots of physicists at the time started looking at that. Suppose they didn't know what the sun was made of, but suppose the sun is made of coal or oil or something like that. Well, they kept deciding that there wasn't enough mass there for it to burn for 100 million or a billion years. So if the sun wasn't that old, there couldn't have been things on the Earth at that time. They knew how much smaller the Earth was. So this became an open question in physics, and lots of people studied it. Lots of physicists studied it, and for the most part got it wrong. So the sun's power output, we've talked about this before, it's called its luminosity. The sun puts out 4 times 10 to the 26 watts. That's joules every second. And so that energy has to come from somewhere, and that's what these guys were looking for. So this English physicist named William Thomson, his rap name, I'm just making a little joke there, was Lord Kelvin. That's what they called him. He was a very famous English physicist whose life was really interesting. It spanned most of the 19th century, and he was really one of the world's greatest scientists of the time. He ended up being wrong about a lot of things later in his life, which many famous scientists were, including Einstein. He and this German guy named Heinrich Helmholtz independently proposed that the sun could be producing all this energy by converting gravitational energy into heat, just like that rock rolling down the hill. And if the sun were continuously, slowly contracting, they argued that there would be enough energy for the sun to burn for about 20 million years, to be that hot for about 20 million years. But not enough energy for it to be hundreds of millions or billions of years old. So they concluded that either Darwin was wrong and the geologists were wrong, or that there was some unknown source of energy involved. Kelvin fought hard to argue that these guys were way overestimating the age of the Earth. He didn't see there was any way that it could be that old, and he argued with them in the newspapers, in print, and tried to shut them up. Darwin was not intimidated, and Darwin said that Mr. Kelvin just hasn't figured out how the Earth can be that old, and it's his job to do so. So it was kind of a standoff. It turned out that in the late 1800s and early 1900s, Marie Curie and Albert Einstein and some others, quite a few others actually, found out that there were enormous amounts of energy to be had in the nucleus of atoms. So chemical reactions don't involve the nucleus. And so nothing before then really had explored the nucleus of atoms. We hadn't engaged in the kinds of science that could explore those types of processes. And so Kelvin and Helmholtz and those guys had no way of knowing. But it turns out that Darwin and the geologists were right. There was another way for the sun to be producing energy, and the amounts of energy were so enormous that it was perfectly reasonable that the sun was hundreds of millions or billions of years old. So the non-physicists won that battle. And so the basics of this is that in nuclear reactions, matter can get converted into energy, and this is Einstein's famous equation, E equals mc squared. That's this one here, and you've heard of it. It turns out E is energy, m is mass, and c is the speed of light. And so if you remember, the speed of light is 300 million miles a second, which is an enormous speed, right? And if we use just 1 kilogram, then it turns out that that 1 kilogram times 3 times 10 to the 8th, or 300 million meters per second squared, that squared is 9 times 10 to the 16th. You end up with 1 kilogram of mass, or about 2.2 pounds, producing 90 quadrillion joules of energy. So, something that weighs a couple of pounds, if you could convert it purely into energy, and this is not what the sun does, but if you could, it would produce enough energy to run 5,000 homes for 70 years. So tiny amounts of mass can get converted into enormous amounts of energy through Einstein's famous equation. And this is kind of what happens in the sun. It turns out that the sun converts about 4 million tons of mass into energy every second. It does this in the process of converting hydrogen into helium. And that's how the sun gets this 4 times 10 to the 26th watts of power. So we're going to talk a little bit about the particles that make up atoms and a few other particles, because these are the ones that are relevant to the discussion of what's going on inside the sun. It'll be fairly simple, I think. The sun's made of protons, neutrons, and electrons, and we've talked about them before. It turns out there are other fundamental particles besides those. But for just a regular atom, these are the ones that are just kind of floating around in there. There are also antiparticles. So the antiparticle for an electron is called a positron. That's just sort of the opposite particle. It turns out if you take a particle and its antiparticle and combine them, they annihilate each other and become pure energy. And so that's a little relevant piece of information. The nucleus of an atom just has protons and neutrons. That's all that's inside it. You might remember they're combined into a tiny little nucleus, right? If you remember, if we drew the atom is the size of a football stadium, the nucleus was a dime at the 50-yard line. So all these protons and neutrons are packed in. Now, if it's a hydrogen atom, it's just 1 proton. If it's helium atom, a typical one, it's 2 protons and 2 neutrons. But if it's uranium, it's like 92 protons and 140-something neutrons. And so it just depends on which nucleus we're talking about. The protons in the nucleus, if there's more than one, they repel each other, right? They're like charges repel. And so something needs to hold them together if they're going to stay together in the nucleus. And what holds them together is this thing called the strong force. Physicists found the strong force. And so we're going to talk a little bit about the strong force because it plays a role in all this discussion. So the strong force keeps protons from pushing each other out of the nucleus, even though they repel each other very strongly. The strong force acts between protons and protons, protons and neutrons, neutrons and neutrons, neutrons and protons. The strong force is stronger than the like charges repel, the proton-proton repulsion force. That force, by the way, is also called the Coulomb force, after a French guy named Charles Coulomb, who lived in the 1700s. He wasn't the first one to suggest it, but he got his name put on it. So the Coulomb force is the one that's causing the protons to repel. The strong force is overpowering it and holding them together. And so it keeps them from escaping from the nucleus. This last fact, that the repulsive, the strong force has a shorter range than the Coulomb force. So the Coulomb force acts over a long range. The strong force acts over a short range, so that if the 2 protons, if they're stuck together by the strong force, if you get them far enough apart, then the strong force will stop acting, and the repulsive Coulomb force will make them run away fast. And so this last fact, that the repulsive proton-proton force has a longer range than the attractive strong force, It's why the periodic table stops. You might have noticed that if you look at a periodic table in your high school chemistry class or somewhere, it has about 100 elements in it and no more. It turns out that's because as the element, you go up the periodic table, the nucleus has more and more particles in it, and they get bigger and bigger. And eventually, they exceed the range of the strong force. And so the repulsive forces are pushing the excess particles away in a way that the strong force can't overcome. And so the periodic table ends at about 100 elements or so. So what about this energy? Well, when particles come together gravitationally, just like the rock rolling down the hill, as it and the Earth get closer together, as it gets closer to the center of the Earth coming down the hill, or if you drop a rock out of the sky, energy gets released. The more and more the rock coming down is gaining energy, and so this is also true when things contract via the strong force. When 2 protons and 2 neutrons combine to form a helium nucleus, energy is released. This energy is called the binding energy, and it's the result of mass getting converted into energy. The individual protons and neutrons weigh less when they're inside the nucleus of a helium atom than they do when they're each out independently by themselves. They have less mass. And so the E equals mc squared equation comes into play as these particles fuse together to form nuclei. Of all the different nuclei, iron has the largest binding energy. And so smaller nuclei release energy when they form large ones up to iron, and larger nuclei like plutonium and uranium release energy when they break up to form something more like iron. So we have 2 processes, one where small nuclei get bigger and release energy, and one where giant nuclei get smaller and release energy. And the first one is called fusion, and the other one is called fission. What happens in the sun is fusion. That is to say, hydrogen atoms combine to make helium atoms. What happens in our nuclear power plants or our atomic bombs, for the most part, is larger nuclei like uranium and plutonium are split by the process called fission, and energy is released in that one as well. It's when you have atoms in the middle somewhere around iron that you can't do anything with them to make energy. And so let's see if we can talk a little bit about, whoops. All right, pause. So let me go through a few of these figures here, and I'll get back to that. Here's the sun, produces an incredible amount of energy. I'm just going to walk you through some of these pictures. Here is Lord Kelvin and Heinrich Helmholtz. They both proposed that the contraction of the sun under its own gravity might account for its energy. It was a great effort, and it got them to a sun that could last about 20 million years, but not far enough. This is our friend Albert Einstein, who passed away in 1955 after a long and glorious life doing all kinds of amazing things. His contribution to this discussion was E equals mc squared, which was just an incidental equation in one of his papers, and other people made a big deal out of it, not really him. This is Wolfgang Pauli, who was the father of the neutrino, which is going to show up here in just a second when we're talking about the reactions that produce the energy in the sun. This is a couple of examples of fusion and fission we were just talking about. So when 2 particles combine, as they do here, this is called fusion. And when a giant nucleus like this one splits, it's called fission. You can sort of think of the green ones as protons and the white ones as neutrons, and they're kind of all mixed up there. And you can, if the strong force only covers a small range, then these guys, the protons up here and the protons down here, are outside the range of each other's strong force, but still repel each other. And that's what splits nuclei up, the larger nuclei up. These explosions, these separations, these fissions, aren't always so clean. There might be one big one and one little one, or a bunch of little bitty protons and neutrons flying off by themselves. The reactions that happen in the atomic bombs were much messier than just this simple picture. And by the way, all the byproducts in nuclear power plants and stuff are sort of like this, and they're radioactive as well. And so that's why you'll hear people talking about, what to do with nuclear waste, radioactive waste. So let's look at what happens inside the nucleus, inside the sun. And in your notes online, I have the equations in here for this. They're also in your chapter. They didn't show up in the version that's in this video, and I'll try to fix that, but you should be able to get to them in the notes online. So inside the sun, this 1H, the 1 means it's just got one proton or neutron, in this case a proton. That's what the 1 means. And H means it's a hydrogen nucleus. So it's hot. These two guys repel each other, right? These two guys, because they're each just a proton, and they don't want to get together, but it's 27 million degrees inside the core of the sun, and that just means these guys are going super fast, and so occasionally they collide in such a way that they combine. Right? And when they do, a certain reaction takes place in which one of the protons spits out a positron, the antiparticle for an electron. It's kind of just losing its positive charge, and it becomes a neutron. And it also spits out this telltale particle that Wolfgang Pauli predicted called the neutrino. The reason Pauli predicted there is another particle here that nobody knew about at the time was by conservation of energy. He set up an experiment, which he could do right here in his laboratory on Earth, in which he fired protons at each other, and he knew how much energy they had. And then he found this deuterium atom at the end, nucleus at the end, that and he could measure its energy. And then he could measure the energy of this positron, and he noticed that the sum of the energy here was not adding up to the sum of the energies here. And by conservation of energy, that law, it should. And so he said, there must be another particle that's slipping away that I can't detect. And sure enough, he was right. Eventually, they detected this particle, and it was called neutrino. And this neutrino played an important role because the number of them and the energy of them was measurable, and it told them that for sure this was, since we can measure the ones coming off the sun, it told them for sure that this was the reaction that was happening inside the sun. And so this is the first step. 1 hydrogen plus 1 hydrogen produces, this is just still a hydrogen because it's got 1 proton, and now it's got a neutron, and so this is an isotope of hydrogen called deuterium. And so now what happens is this deuterium atom, nucleus that we just created, is also flying around there in the nucleus. It hits another hydrogen atom. These guys combine to form what we call a helium-3 nucleus. It's helium because it's got 2 protons. These blue guys are protons. And 1 neutron. And so it's helium-3. 3 means it's got 3 total protons plus neutrons. And a gamma ray. That gamma ray is just a light ray that's carrying away a lot of energy. That's where part of where the sun's energy comes from. And so now I've got a helium-3, but this is just step 2 of the process. And so now this helium-3 eventually bangs into another helium-3, and they produce, oops, I lost something there. Sorry, so these 2 helium-3s here, these 2 guys, there's a total of 2 protons here and 2 protons here, and then a neutron between, so we've got 4 protons and 2 neutrons. That produces a helium-4. This is a standard helium nucleus, a garden variety helium nucleus, and then we get another hydrogen back, another hydrogen back. And so in those 3 steps, we got, we turned 4 hydrogens into 1 helium-4. And this 3-step process is called the proton-proton chain that converts hydrogen into helium. in addition to this process, energy is produced through the gamma rays and kinetic energies in these particles and so on, and that's where the energy from the sun comes from. I think, let's see, so, let's see if I got this right. Yeah, this is a key to this. And so all my variables are left out of here because the explain everything isn't getting my font in here. And so this section is just defining the different terms and the equations that didn't show up a bit ago. So look at these sheets in your notes and you'll see what I'm talking about. I think it's all explained pretty well in there. So in general, what the sun is doing down here is converting every second. The sun is converting 600 million tons of hydrogen into 596 million tons of helium every second. And then in that process, those remaining 4 million tons of mass are converted to energy in a second. And that's where the 4 times 10 to the 26 watts comes from. This energy, this much energy that's lost, that much mass, which is lost in the process of converting the hydrogen to helium, is all getting converted into energy, which is released by the sun. So that's basically how the sun works, how all stars work. Very massive stars have like a shortcut to this process, but we won't talk about that right now at least. So this says, describe the state of equilibrium of the sun. So what's going on inside the sun is that it's got this enormous gravity that's trying to crush everything together. But it compresses itself, and just like Kelvin and Helmholtz said, it heats up as it contracts. Well, eventually it heats up enough so that the core gets hot enough so that fusion can take place. And that fusion stops the contraction because there's outward pressure from all the energy coming out of the fusion process, balanced by the gravity that's crushing inward. And so the sun is kind of in just an equilibrium state in which gravity and radiation and nuclear fusion pressure are kind of at a standstill. So let me go back to a few of the pictures here. So this is particles bouncing around. The faster they bounce, the more pressure they create, and that's what's going on with the fusion. Gravity is trying to cause these particles to be crushed together, but they're bouncing around here, preventing that from happening. And so what you have is sort of a hydrostatic equilibrium, we call it, in which get that out of there. Well, I'm not doing a very good job of that. In which gravity is pulling in and there's pressure pushing out, and the sun just sort of stays in its position for a long period of time. Actually, the sun is slowly getting a little larger, but very slowly. Rising convection currents carry the heat to the sun's surface. We've talked a little bit about this. Nothing is perfectly simple, but the sun's interior heats this convection zone, which carries the heat up to the top, which is then released. It takes about somewhere between 100,000 and 1,000,000 years for energy from the core to get to the sun's surface. So the energy that we're getting from the sun right now was from fusion that took place hundreds of thousands or millions of years ago. So this is a nice illustration of what happens inside the sun's core. Photons interact very strongly with all the particles in the sun, so it takes them forever to work their way out, or that heat to work its way out. It's got to work its way out of the core, and then it's got to work its way through the radiation zone. And then there's actually a convection zone in there that we saw a minute ago, and then it can leave. Neutrinos just leave. They interact very weakly with matter, and so we get the neutrinos almost straight from the core. It doesn't matter too much, except because they don't interact much, they aren't changed very much, and we get to see them just as they were when the interaction took place, and that's what allows us to conclusively believe that, or show that the neutrinos that come out of the sun's core are the exact same ones we get, same energy and so forth, when we simulate what happens inside the sun in a laboratory. So this is sort of our picture of the sun here, with a radiative zone and a convection zone like we saw a few chapters ago, and here's a sunspot. So these are 4 charts of sort of what's going on inside the sun. This graph is temperature. In each case, the horizontal graph, the left corner here is the center of the sun, and it goes from 0 to 1 solar radius. So this is like right at the bottom of the photosphere, what we would call, just underneath the atmosphere. We might call that the surface of the sun, but technically it's not, of course. The sun doesn't really have a surface. And so it's got the core where nuclear fusion takes place, then it's got a radiative zone, and then it's got a convective zone, and we can see the temperature, 15 million in the core, 5,800 at 5,800 at the surface. So it's way hotter in the core than it is the surface. This is where the fraction of the sun's luminosity is. Remember, the luminosity is just the energy per second. Notice it's almost all produced inside the core. 100% of it at the top here is already produced by the time you get to the radiative zone. No additional energy is being produced out here. It's all the actions happening inside the core. Over here, same graph, except the density. The density in the core of the sun is 160. Remember, the density of water is 1. We said the average density of the sun was 1.4. The stuff way out here is way below that. The stuff way in here is way above it. 160, so the density of gold is about 19 grams per cubic centimeter, and so the core of the sun is the center of the sun is about 10 times the density of gold. By the way, there are objects that are way more dense than that. Finally, this last graph is the percentage of hydrogen by weight. Notice in the core, the percentage is the lowest, and that's because the sun is slowly turning hydrogen into helium, and so the very center of the sun has the most helium, and so the least amount of hydrogen, and then as you go out, it's roughly 75% hydrogen and 25% helium. Slowly, the hydrogen is getting converted into helium inside the core. That's the action that happens inside the core. Let me see if I can... I want to go the other way, sorry. So we talked about the strong force, talked about the sun's interior a little bit. I said it takes about 100,000 to 1 million. The sun is hottest at its core, its densest. I think we talked about that. It turns out the sun pulsates. That's what that picture was showing you just looked at. Let me just go ahead and pull it back up. These red and blue circles are the surface of the sun moving up and down. We can look at Doppler shift of the surface of the sun, the bottom of the sun's atmosphere, the top of the photosphere, and we can see that the sun is oscillating. And it turns out that oscillation, the in and out motion of those areas there, tell us what's going on inside the core in the same way that earthquakes tell us what's happening inside the earth. It's not perfect, but it gives us a lot of useful information. For example, the differential rotation that we talked about inside the sun is going on in the core as well. And so it's not just happening at the surface. Differential rotation, in which the core is turning faster than the poles, continues in the interior of the sun. So the last thing in the chapter is the solar neutrinos, which helped us understand that the reactions going on inside the sun are the ones we think they are. This problem, by the way, wasn't solved until about 20 years ago. Early experiments were done in the 1960s, so 60 years ago. And only in the last couple of decades have we really nailed down the processes that are happening inside the sun and been able to replicate them in a laboratory and really conclusively show that we know how the sun is producing its energy.